Hello everyone, myself Pranay Sarkar and you are watching ChemPro YouTube channel. Please watch the complete video and don't skip. I promise you will get extra and learn the topic like never before. Today our topic is parallel reaction. Then let's start. Parallel or concurrent reaction. This is a very important reaction from chemical kinetics, and several types of important questions are asked in CSIR, NET and GATE examination. Okay, and in this video we are going to derive the important formulae and we will solve some problems from this topic. Okay, so in parallel reaction, A is simultaneously converted into B and C. So at time equal to 0 or initial state, when the t equal to 0, the concentration of A is A0, B is 0 and C is 0. At time t, the concentration of A will be A, for B it will be B, and for C it will be C. So we can just say that the net rate of consumption of A, it will be the rate of consumption of A in step 1, that is the step where A is converted into B, plus the rate of consumption of A in step 2. Okay, and this is the step where the A is converted into C. Okay, so from this we can just write that the rate of consumption of A, that is minus dA over dt. Okay, and it will be equal to the K1A plus K2A. Okay, and from this we can just get common of A and can write that the dA over dt into equal to concentration of A in first bracket K1 plus K2. Okay, so we will do integration of this, and that will be integration over A0 to A dA upon dt equals to the constant part, that is K1 plus K2, integration of 0 to t into dt. Okay, so from this we can get minus ln A by A0 equals to K1 plus K2 into t, or we can write that ln A0 by A equals to K1 plus K2 into t. Okay, so we can just memorize this integrated form for the parallel reaction, and from this we can also write that from this equation we can also write that ln A by A0 equals to minus K1 plus K2 into t. Okay, and from this we can just calculate the concentration of A, that will be A equals to A0 into e to the power minus K1 plus K2 into t. Okay, and this is very important formula from this topic, that is the concentration of A. Okay, this is the concentration of A, that is equal to the A0 into e to the power minus K1 plus K2 into t. And this formula is quite similar to the first order reaction where A is, or a reactant is, converted into product. Now we will derive the rate of formation of B. Okay, the rate of formation of B, and from this we can derive the concentration of B. Okay, so the rate of formation of B will be dB upon dt equal to K1A. Okay, and from this we can just write that dB upon dt equals to K1, and from previous derivation we can get the value of concentration of A, that is the A0 into e to the power minus K1 plus K2 into t. Okay, so from this we can write dB equals to k1 a0 e to the power minus k1 plus k2 into t and into dt. Okay, so here we can just do the integration from 0 to b. Okay, and from this we can just do 0 to t. Now from this we can get that concentration of b equals to k1 a0, and from this part we can get that e to the power minus k1 plus k2 into t, and this will be value from 0 to t, and by minus of k1 plus k2. Okay, and by putting the value of the limit we can get from here that concentration of b equal to k1 into a0, and it will be the e to the power minus k1 plus k2 into t minus 1. Okay, and pi minus k1 plus k2. Okay, and from that we can get concentration of b equals to k1 by k1 plus k2 into a0. Okay, here a0, and here 1 minus e to the power minus k1 plus k2 into t. So this is the formula of concentration of b. Okay, that is concentration of b equals to k1 by k1 plus k2 into a0 into 1 minus e to the power k1 plus k2 into t. Okay, so from this we can write the formula of concentration of c. That is similarly we can write concentration of c equals to, so from the previous slide we can get that the A to C, for the A to C reaction, the reaction constant is K2. So here in this formula we have to just change this K1, this K1 by K2. So the formula will be K2 into A0 by K1 plus K2 1 minus e to the power minus k1 plus k2 into t. Okay, so this is the formula for the concentration of c. Okay, this is the formula of concentration of c. So these two formulas, or these two formulae, are very important. Okay, are very important. Now if we do that concentration of b by concentration of c, so from this we can get that k1 by k2, because all the terms including a0 and k1 plus k2 and this all the term will be cancelled out, and we can get this formula, that is concentration of b by concentration of c equals to k1 by k2. If the reaction is given like this, that is a to 2b and a to c. Okay, and the reaction constant for this is k1 and for this is k2, and we have to find out the concentration of b over concentration of c. So what will be the value of this? So for this we will write that the formation of b is like dB by dt equals to 2 into k1 into a. Okay, so for the previous reaction, the formation of b is like dB by dt equals to k1 into a. Okay, and because of the coefficient is 2, here we should include the 2. So now we can write the formula of concentration of b like 2 k1 into a0 by k1 plus k2 into 1 minus e to the power minus k1 plus k2 into t. Okay, into t, and for c it will be the k2 into a0 by k1 plus k2 into 1 minus e to the power minus k1 plus k2 into t. So from this we can just write that concentration of B by concentration of C equals to what? That 2K1 by K2. Okay, because of the coefficient of B, we must include that the 2. Okay, now if the reaction is given like this, that is A2NB and A2MC, and the reaction constants are K1 and K2. So what would be the concentration of B and concentration of C? So like this, we have to include the coefficient, that is M and N, in the formula. Okay, so for that we have to write the concentration of B like N K1 into concentration of A0 by K1 plus K2 into 1 minus e to the power minus K1 plus K2 into T, and the concentration of C will be, here the coefficient is M, then M K2 into A0 by K1 plus K2 into 1 minus e to the power minus K1 plus K2 into T. Okay, so from this we can write the concentration of B over concentration of C just like N K1 by M K2. Okay, so for the given coefficient of B and C, like M and N, so we have to include the N and include the M in the formula of concentration of B and C. If the reaction is given like A is converted into B into C and as well as into D, and the corresponding reaction constant are like K1, K2 and K3. So we have to find out the concentration of A and the concentration of B. So now what we will do? So for this we can write the consumption of the A like dA minus dA by dt equals to K1A plus K2A plus K3A. Okay, and from this we can write minus dA by dt, and we can do A into K1 plus K2 plus K3 into T. Okay, so from this we can write that minus dA by A equals to K1 plus K2 plus K3 into dt. Okay, so here the, okay, so after doing the integration over A0 to A and here 0 to T, we can get minus ln A by A0 equals to K1 plus K2 plus K3 into T. So from this we can write the formula of concentration of A is like A equals to A0 into e to the power minus K1 plus K2 plus K3 into T. Okay, so we have to write all the reaction constant in the formula. Okay, so for this we have to write the concentration of B. So here we will include all the reaction constants. So the concentration of B will be like K1 into A0 by K1 plus K2 plus K3 into 1 minus e to the power minus K1 plus K2 plus K3 into T. Okay, and this will be the formula for B. Okay, this will be the formula of B. Now if it is given like this, okay, so this is A, and from A it will be converted into B into C and dot 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 up to N. Okay, so if the reaction constant is like K1 K2 and up to Kn, then what will be the formula of A? So for this the concentration of A will be like A0 into e to the power minus K1 plus K2 plus dot 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 up to Kn into T, and for this the concentration of B will be like K1A0 by K1 plus K2 plus K3 plus dot 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 up to Kn into 1 minus e to the power minus K1 plus K2 plus dot 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 up to Kn into T. Okay, into T. So this will be the formula. So now we have to calculate the maximum percentage of yield of B and C. So from the parallel reaction, that is A to B and A to C, we can have the concentration of A consumed at time T equals to concentration of B plus concentration of C. So from this we can write the maximum percentage of yield of B, that is concentration of B at time T over concentration of A consumed at time T into 100. So from this we can write concentration of B by concentration of B plus concentration of C, and this from this equation and into 100, or we can write another form that K1 by K1 plus K2 K2 into 100. Okay, so this will be the form, and for C the formula will be the maximum percentage of yield of C. It will be concentration of C by concentration of B plus concentration of C into 100, or K2 by K1 plus K2 into 100. Here this is a question from CSIR-NET June 2019, and the question says that the gas phase reaction decomposition of A at 1000 Kelvin follows two decomposition paths. So at first A2 B plus C, and in second path it is A2 P plus Q, and the rate constant for the two paths are 3 second inverse and 5 second inverse. So we have to calculate the maximum theoretical percentage yield of P. Okay, so we have to calculate the maximum percentage of yield or maximum theoretical percentage yield for the P at 1000 Kelvin. Okay, so for that we have the reaction like this: A to B plus C, and from A it is P plus Q. Okay, and here it is K1 and here it is K2, and it is given that K1 is 3 second inverse and K2 is 5 second inverse. Okay, so for P, it will be the maximum percentage of yield of P. It will be K2 by K1 plus K2 into 100. So it will be very easy that K2 is 5 by 3 plus 5 into 100, and the answer will be 62.5. Okay, 62.5, the maximum percentage yield of P. Then the correct answer will be option 1. Okay, 62.5, this is the correct one. Now next, here is a question from GATE 2019. Okay, and the question says that consider the following two parallel reversible first order reactions at temperature T, that is P2Q and P2R, where K1 and K2 are the this K1 and K2 are the rate constants, and their values are given like K1 for K1. Okay, for K1 the value is given 5 into 10 to the power minus 2 minute inverse. Okay, and for K2 the value is given 15 into 10 to the power minus 2 minute inverse, and respectively at temperature T, if the initial concentration of P, that is the 4 mole per liter, then the concentration of R, then we have to calculate the percentage of R. Okay, so here the K1 and K2 are given, and the initial concentration, that is the P0 is given 4 mole per liter. Okay, so for this concentration of R will be, from the formula we can write K2 into P0 by K1 plus K2 into 1 minus e to the power minus K1 plus K2 into T. Okay, now, and here it is given that the time is 10 minutes. Okay, So the time is 10 minutes here. So now putting the values, that is K2 is 15 into 10 to the power minus 2, and for P0 it is 4 by K1 plus K2, that is we can write 5 plus 15 into 10 to the minus 2. Here we can just get common the 10 to the minus 2 from this K1 and K2, and we can write like this. And here 1 minus e to the power minus what 5 plus 15 into 10 to the power minus 2 into 10, and by calculating this we can get that 60 by 20. Okay, 60 by 20. 60 by 20 into 1 minus e to the power minus 20 into 10 to the power minus 1, and from this we can get 3 into 1 minus e to the power minus 2. Okay, and by putting the value of e to the power minus 2 we can get 1 minus 0.1353. Then ultimately the answer is 2.59. Okay, this is the answer. So, and it is given that we have to round up to the 2 decimal places for the concentration of R. So here the answer is concentration of R is 2.59. This is the final answer. Thanks for watching the complete video. If you really enjoyed, please like the video and subscribe the channel to motivate me, and hit the bell icon to get all the notifications. And if you have any suggestion or query, please comment down below.